Hey guys, it's Mr. Sheelane here. This is going to be the the rest of the notes for the Unit 6.1 Uniform Circular Motion notes. Last time we left off right here at the forces in circular motion. Before this, we were looking at just strictly how it is that we can calculate the tangential velocity when we have an object moving in a circular path, and then also the acceleration, specifically the centripetal acceleration that we observe from that object as it's moving on that circular path as it wants to move towards the center. Basically, just this picture up right here. Okay, now what we're going to be getting into today is going to be pretty much these three pictures right here. Is okay, we've got velocity, we've got the acceleration moving towards the center. Okay, well, what about the force? Because obviously, if you have some sort of acceleration moving towards the center, you have to have some sort of force that's also moving towards the center, which is exactly what we're going to be doing. So let's get right to it. So analyzing forces in circular motion. So thinking back to Newton's laws here, specifically Newton's second law, there has to be, has to be some sort of net force acting towards the center of the circle that causes this centripetal acceleration, because as Newton saw was that, the acceleration is due to a force divided by its mass. So in this case, if we have acceleration, we have to have somehow force on the other side of that. Okay. And so what we can derive out of this is that we can derive this, okay, using basically taking the centripetal acceleration equation and then merging it with just a simple force equation. Force is equal to mass times acceleration. We can come up with a way that we can measure the amount of centripetal force that is moving towards the center. So the equations for centripetal acceleration involving the period and the frequency of circular motion can also be combined with the second law equation, which is what I basically just said. So thus, there are three common ways of writing the equation. So these are the three ways. So right here, this is here. I'm gonna use. So right here we have this is the equation. Oh boy, that is a nasty looking circle. But this is the equation that I was just referring to. So this right here, this is the centripetal acceleration. Well, I guess they're all three of them centripetal acceleration equation. So I guess that's kind of a moot point here. But this one is where it's just a simple tangential velocity squared over the radius, which is just centripetal acceleration, multiplied by the mass of your object. Okay, perfect. That's pretty straightforward. Here is the equation where we have period, okay, because we know it's period because of the t down here. But notice this. Notice that the mass has been inserted into the equation here. So now it isn't just 4 times pi squared times the radius divided by period squared. It's now 4 times pi squared times the mass of our object times the radius divided by the period squared. And then finally, we have the third one over here. This third one is literally the same thing. We've got mass that's kind of tucked away in the center here, so don't forget about that. But it's just, in this case, it's just the frequency. And remember from the last set of notes, frequency and time are the reciprocal units here. Period being the time it takes in order to make one full revolution. Frequency is the number of revolutions that an object makes within a particular time. Okay. So we're going to expand on especially add in some new. We're going to be adding in some new. Units here, specifically and mostly for frequency. So, and hopefully you've seen them before. Maybe you didn't understand what they were, but you'll have a sense of what these are. And especially it'll be a nice way to when we move into waves and when we move into sound, you'll be somewhat familiar with some units but when we get there. But that's not until fourth quarter. Okay, it's still a bit of ways away from right now. So anyway, those are the three equations. So, and you could sum this up to this, that sigma F, or the sum of all forces, your net force, is the magnitude of the net force that causes the circular motion. Okay. In other words, this is your centripetal force. Okay. So we've got this check your understanding number 5, and I believe check your understanding number 6, which I get into in the other videos, it'll be in the next check, or it'll be in the next video I'll put out, which will be the check your understanding video. That'll be part of the assignment post here in Google Classroom. But before I move away from this, let me double check here. Let's see. Yeah, number 6. This is where those notes come in, or where these new units come in. So notice right here. So hertz. Okay, Hz. So that's what I was just referring to a little bit ago. Frequency specifically is going to have, we're going to be denoting frequency with the units of hertz. Every now and again, I'll just say for right now that this is not going to be something where I'm going to rely on you to put down the correct, hertz, because for the most part, we're going to be working with the number of revolutions per second. And hertz we get into later on we get that into later on in sound, but just be aware that these will pop up here and there, and don't worry, they'll be figured out and solved for you, because I won't have you understand what this is until we get to that 4th quarter material, when we get to sound and waves. Okay, so don't be too spooked about it. So when you do see hertz, when you do see it, it's pretty much always going to be followed up with saying that at a frequency of blah 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 hertz. Okay, so don't be too spooked about it. Okay, also not a bad idea. Just Google it. I'm serious. We won't get into it till 4th quarter material, but if you're seriously curious about it now, Google it. See what hertz are. See why they're called hertz. Okay, so anyway, so just be prepared for that. Watch out for that. Okay, so centripetal forces. So this is just a visual breakdown of basically what we've already covered. Now, there's some funny symbols here. So we've got this funny symbol omega over here, and we haven't really talked about that. All you need to know what this is that this is pretty much just the angular velocity. That is something that we do not get into. That would be more AP material, because that's where you need to know how to calculate that using radians. We bypass that. We get past that. But in this image, they include it. So that's just not to spook you too much about this either. You won't have to know what that is. You can just kind of ignore that guy. But let's kind of continue to look at what the rest of this is. So centripetal force, for particular modes of movement, of motion, can also equal the force of friction. So this is especially true when it comes to cars. So there's a reason why this word is here, axis. So what we're basically looking at here is we're basically looking at a crude drawing of, say, like a wheel, like a tire. Okay. And so what we can realize and what we can put together in this is that the centripetal force is equal to the force of friction. And we're going to be practicing this in class. The day that I'm doing this in class, we're practicing this. But anyway, it's a neat little thing that where we can solve for centripetal force of a moving object, specifically a wheel that's in contact with the ground. And what we can do here is that we can more or less combine our two force equations here as a way to show, like, hey, yeah, centripetal force, no different from the force of friction. They're both moving towards the center of the object, or towards the axis, the pivot point, the point of attachment of a particular object. So what this turns into is that you would see that again, this is going to be the equal to this. Now, notice, we are not working with kinetic friction here. So you have to ask the question, well, Mr. Sheeline, why are we not working with kinetic friction? Because I thought kinetic friction was friction of a moving object. And you're exactly right. However, the only difference was like objects that we were looking at were like this. So my goodness, that is a terrible floor. Try to work with the mouse. I'm not as good as Saul is from Khan Academy, but we were working with this. We're working like with an object that, you had your gravitational force going down, you had your normal force going this way, you had your applied force going this way, and then you had your friction force. Oh goodness, you had your friction force going this way. So here's your friction force. Oh my God, here's your applied force. Okay, and so while we were moving this, the entire object is in contact, right? I should say the portion of the object is in constant contact with the floor. Okay, so because of that, we can use kinetic friction because the surface of this object and the surface of the floor do not cease to be. They are always in contact with one another. Think about a wheel though. When, let's say, if we're moving in this way, okay, like the picture indicates, if we're moving this way, this part of the wheel right here, that part of the wheel is only going to be on the ground for not even a second, especially if we're moving at a pretty quick pace. So if we have an object that is, in this case, in what's actually called, I actually won't get into what it's really called, but when we have an object that's rotating in this fashion, the point of contact where friction is coming into contact with the ground is so quick and so instantaneous. It's as if that point of the object, in this case a wheel, is standing still. So in this case, for wheels, we will use friction or static friction of a non-moving object, okay, which does seem kind of weird. But when you think about it, remember, any point on this, any given point on this wheel here that is moving, our velocity is the same. Well, with uniform circular motion, it's the same. Okay, and it's moving in the same direction. It's moving tangential from the surface of our circle, but all at the same time, it's all at different. It's all at different directions. Okay, so in that sort of idea, which I know this is a long-winded way of saying this, but in this sort of idea that because our velocity is always changing directions, so is our friction force. And because our friction force never actually gets to maintain our friction force does not get to maintain the surface contact between the floor and itself, we have no use of kinetic friction. We can only use really static friction. So notice that, okay, is that we're working with static friction here. So we're going to use the static friction coefficient, and it's just multiplied with the normal force, okay? Because, again, these two things are the same thing. So what this can turn into is let's try this out. So the mass times the tangential velocity squared divided by the radius is equal to the static friction coefficient times the normal force of our object. Okay, and we can use this to solve for a number of things. We can solve this to figure out maybe what the coefficient is. We can figure out what we're going to be doing a lot of the time is to figure out the velocity. And so that's, again, long-winded way of why we're pointing this out here is that for moving objects, specifically objects on an axle, such as a tire or a wheel that are making different points of contact at different times, on a particular surface, i.e. a car rolling forward, we will use the mass of the car. We're going to use the radius of the wheel. We're going to use the static friction coefficient, and we're going to use the normal force of this particular object in order to find out how quickly the outside of the wheel is moving as it's moving along. And we're going to take a look at that at at this problem in class that we're going to do. I'll probably maybe post a video. Yeah, actually I will. I'll post a video on what that'll look like, that little assignment, in case anybody is absent. So anyway, recap on this one slide. Centripetal force can equal the force of friction, so the centripetal force is equal to the static friction force that we see that is also moving towards the center of a circle. Specifically speaking, when we're looking at something like a wheel, something like a tire, okay, that's making contact at different points at different times on this object, okay? So here we're going to use this with cars. So, okay, what forces can cause something to move in a circle? Really, any of them, okay? Any of them: drag, friction, gravity, normal, tension, thrust, okay? So any of them can do this, that can cause something to move in a circle. And so what that means is that any one of these can be equal to the centripetal force. So when you participated in that little engagement activity, when you spun the rubber stopper that was attached on the string. So when you were spinning that, vertically, well, what was that centripetal force? Well, that centripetal force would have been tension force. Okay, the tension force would have been equal to the centripetal force that was moving towards the center towards your hand, where you were holding and spinning the rubber stopper. Okay, where else did we see centripetal force equal one of these other forces? When you had the marble, the ball bearing spinning in the plate before you did that, well, that was a normal force. The normal force was equal to the centripetal force on your particular plate. Okay, all that stuff, man. And it just depends. And then, as we just talked about, the friction force would be a great example of where the centripetal force is equal to the friction force is, say, a wheel or tire moving across the ground. Okay. So these are all great examples, and all of these can be attributed and can be equal to centripetal force, but it does depend upon the situation. And we're going to be practicing that and taking a look at, or actually we did practice that, and you did take a look at that, in a previous assignment. Or no, you will be looking at that. My bad. You will be looking at that at the assignment I'm going to pass out today. Well, today, but we're doing this. Okay. Oh, and that just made me realize that this is, so what I just mentioned, the car activity that I said I'd make a video for, now I'm confusing you guys even more. That's going to be on the next in-person day. So completely ignore that. When we're 2 slides back, just whatever. You'll see when you're in class. So, all right. So anyway, these forces can be used to constantly counteract the body's desire to move away from the circular path on a tangent. So what that means is you have your object on the outside, and it wants to move tangentially from your circular motion here. And the force is saying, no, I want you to go towards the center. I want you to go this way. Why are you doing this? Okay. But good thing in this case, because, man, try to imagine what that looked like if this and this were equal to one another. But in this case, because it obviously can't overcome the tangential velocity here, there's too much inertia here, that the velocity counteracts the centripetal force, and basically it's just you do have the center force here, but your object will continue along its circular path. Things would be very, very different if that wasn't the case. But obviously that you do have to overcome this in the first place. You can't pick up a 1,200 kilogram, object and all of a sudden start spinning it thinking that you're able to keep it in a circular path away from your centripetal force. No, you need to overcome the centripetal force first. But anyway, so, and then just a reminder, all forces that are center seeking are centripetal forces. Okay. So what this last point basically is trying to tell you here is that centripetal force is not a particular kind of force like drag, like friction, like thrust or applied, like tension. It's not its own thing. It's a way that we can describe those specific kinds of forces as this, that it's a center-seeking force when we are dealing with circular motion. Okay, so that's what it is. Now we get to talk about a very, very strange, non-existent-ish kind of force. So there's something that counteracts the centripetal force, and it's called the centrifugal force. So this force describes a tendency of an object following on a curved path to fly outwards, away from the center of the curve. Now, the only problem is that it's really not a force. It's something that we really can't measure. Well, you can measure it to a certain extent, but it kind of doesn't exist. So, excuse me. Well, it's more of a way to describe the motion and the motion and the consistent nature of objects that are moving in a uniform circular path. That's really what it is. But we call it the centrifugal force just to give it a name, really, and to show that, well, there's something that's kind of opposing seemingly opposing the um, uh, centrifugal centrifugal force here. Or centripetal, sorry, centripetal force here. So it results from inertia. In other words, the tendency of an object to resist any change in its state of motion. So it's really this weird force that describes, again, the motion of of an object that's in the circular path. Okay. So again, centripetal force is a real force. Okay. It's something that we can measure. It's something that does exist because we can measure the acceleration towards the center of the like the center point of the attachment, or the center of whatever the circle is. And it's somewhat counteracted, or at least seemingly counteracted, by the centrifugal force that prevents that object from flying out and keeping it moving in a uniform speed along a circular path. Okay. So it would pretty much kind of look like this if we were to kind of put it into a picture here. So here we have a car that's moving in a circular path here. So clearly here is the tangential velocity that's occurring around the circular path. Here is your though it is quite exaggerated here, the centripetal force here. Your centripetal force is quite exaggerated, but it's still moving towards the center. Okay. And then here is what we would refer to as a centrifugal force. It's the one that completely opposes. So if I were to overlay this over here, it would look, like this, that you would have, here's your centrifugal force. Okay. So centrifugal force, centripetal force, tangential velocity. So again, this guy doesn't really exist. That force does not really exist. It's more of the idea that this guy is maintaining its good old inertia. Also, you in the car you are also maintaining your inertia of both moving in this direction and also being pulled in this direction, which then creates your path here. But there is this little guy here that also counteracts this a little bit, in order to, excuse me, to allow you to stay on that path, so you don't just fly straight forward, so you just don't get sucked into the center. Okay, so again, it's really just talking about inertia, though. So always keep that in mind. And I'll have a demo in class one day about this. And hopefully, if you're absent and watching this, hopefully you'll be there for that day. So, and that's pretty much the end of the notes. So I will post this video along with the assignment post, or this material post for this particular day that we're going over the notes. It's a neat little video about this Canadian. That's a Canadian guy in his TV show up in Canada. He goes to an aerospace center, and he participates in the basically their training for astronauts, training for pilots, where they use centripetal force, where they use centrifugal force, and measure both of these to the extent that they can, in order to train people for heavy amounts of gravitational forces, or G's, while they're in, say, jets, or if they are in spaceships. Okay, so we're going to play this in class. I'll post this with the assignment posted. You can watch it on your own there. And that's pretty much it, guys. Remember, there is a couple of check your understandings. Okay, there are a couple of check your understandings for you to complete, so make sure you complete those as well. Give those a whack, and I will have a video posted that will show you how to calculate those properly. So anyway, that is the end of that. So if you guys still have any questions for me, make sure you ask me any questions that you may have. If not, then I'll just see you in the next one.